Y agregar el tema de los
Yeah, yeah. No worries. No rush.
And how about did you hand in?
No, it's today.
Ah, yeah, it's today.
We're handing the
At 4 or?
I think it's at 23:59.
Ah, okay.
So we have all day.
Now you can start.
But it's almost done. It's only minor.
Done well or done there is something.
Done like this is all we can do with the time we have.
Okay.
En realidad yo entré tarde. Entré tarde. Era un proyecto que partió el Felipe, en Santibáñez, con la cara. Y yo entré como hace la semana pasada, hace 2 semanas. Es una plataforma para
No, es que realmente lo que pasa es que el catálogo es muy constante, pero yo empiezo a hacer eso. Me teste que mire como las expresiones que tienes, las organos de mama, en tumores, y en base de eso, está
You can start.
Okay, thank you very much for coming. We are starting almost Swiss time.
Almost Swiss time, yeah.
But it's quite on time for the Chilean typical starting time. So I'm very happy to have Reto, who came back from holidays just to talk to us today. Well, you are saying the rest of the week.
Yeah.
But Reto started the 6th of April in the faculty. I checked.
Exactly, yeah.
And it has been a real pleasure to have you here.
Thank you.
Interesting discussions and in general, like a very easy person to have around because you just work and are focused all the time. So it's amazing. So for the Germans here, well, you can have an example of someone just coming and working hard and traveling. It works.
And leaving.
So he's presenting his thesis that he's developing in Heidelberg, Heilbronn, and he has prepared like 40 minutes or something. But the idea of these talks is that you can interrupt while he's talking and ask questions. Thank you.
Perfect. So thank you very much for this nice introduction. I'm really happy to be back here in Santiago and to have the chance to present today my master's thesis, the final results, but I'm also happy that you guys from Germany are here too, that I can show you my results, what I've done in the last 6 months here in Santiago, and maybe it can also be like an inspiration for you, what you want to do with your master's thesis, or even if you want to apply as well to write your master's thesis in Santiago. I can tell you it's a really nice experience, so if you want to do it, you really should. So as you can see, the title of my thesis is Real-Time Body Temperature and Heart Rate Monitoring System for Classification of Physiological Response Patterns using Wearable Sensor and Machine Learning Technology. And I guess we will just start with the motivation. So nowadays, like everybody has a mobile phone, a mobile device, and these devices become more and more an integral part of our lives. And the good thing about these devices is that some of them have like sensors which you can use to record health data. So this facilitates really the continuous monitoring and analysis of personal vital signs. But of course, it's not that simple. Normally, the analysis and interpretation of this data is quite challenging because these physiological response patterns, they can vary from person to person. They are like dependent on activities, diseases, the environmental context, but also on things like demographic factors, the age, the gender, the fitness level. So in conclusion, that means that you cannot describe physiological response patterns as in general terms, but there's like one solution what you can do, and that is you can use machine learning algorithms which like try to interpret and learn a person's individual response pattern. So from this motivation, we derived my hypothesis, which is a real-time body temperature and heart rate monitoring system enables personalized classification of physiological response patterns as either normal or abnormal. So that was what I was trying to do. And if you like start to develop a system like this, there are always or normally like challenges. And there are two really important factors which can influence the accuracy, the sensitivity, and the specificity of such a system. First of all, the system is really dependent on the quality of the sensor you use. So if you have bad data, there are no algorithms which can work with bad data, because if the data is bad, the results will be bad too. And second, the performance of the algorithms is also really important. So if you have algorithms which cannot work with your data, there will be no good results, and in the end, you cannot use it. So when I started to work on my project, I really had to take this into account when I derived the thesis objects from my hypothesis, and I came up in the end with 5 objectives which I wanted to like fulfill in the end. That was first to evaluate the measurement quality of the sensor I chose, and therefore to show that it's suitable for real-time detection of changes in vital signs. Then I wanted to develop a concept for a real-time distributed monitoring and classification system, and then in the end, of course, implement this concept in a prototype. And finally, to show that machine learning algorithms can be used for the interpretation of personal vital signs, and in the end also to show that they can classify tendency changes of vital signs in response patterns as either physiologically normal or abnormal, which is like the ultimate goal of my hypothesis, right? So for the rest of my presentation, I will go just through these 5 objectives and show their results and discuss them right away. So let's start first with the sensor I chose. The sensor I chose was the Cosinus 1. It's a sensor which you wear in your ear. It can measure body temperature and heart rate. In my evaluation of the sensor, I only made the body temperature evaluation because heart rate evaluations were already done by many professional sports people, and they showed that the heart rate measurements are really like very accurate. So I focused on the body temperature, and what you can see here in the first figure is that the sensor needs around 4 to 6 minutes. It depends a little bit on the environment until it measures the body temperature in a range which is normal for a human. So that was the first analysis what I've done. Then the second one is I tried to see how the environment, like the temperature outside, inside, sun, wind, rain, can influence the measurements. And so that's what you see here. First of all, that was inside the building upstairs. We have like a normal measurements, but then when I went outside, it was winter here, it was really cold, so the body temperature, or the measured body temperature, started to drop until like 33.7 degrees, which is already really low for a human. And then, but when I went into the sun again, the body temperature or the measurements started to rise again, same, going out of the sun, going inside of the building. So that shows actually that the measurements of the Cosinus 1 are not really accurate. It's really dependent on the outside temperature or the surrounding temperature. Then next, I also tried to compare the measurements to a commercially available thermometer, how you can buy it in every pharmacy. And that's what you can see here on the blue line. So it's really a steady line which measures the temperature correctly. On top, you see the Cosinus 1 measurements, which have really like fluctuations, which show you that you actually have a belt of inaccuracy as well when you do the measurements with the Cosinus 1, which is not really what you want to have. The difference between these two lines is actually, or probably because you measure the temperature on different positions. So if the cosinus 1, it's in the ear, with the digital thermometer, it's under the armpit. So that is probably the reason why it's different. But also, I compared, together with the help of Stefan, the cosinus 1 during sports on an electric trainer. And on top, you can see again the digital thermometer, which is accurate, which shows actually what the literature describes as well. You have, when you start with sports, you have a rise of body temperature, and then it's like continuous and falls again after finishing. And the measurements of the cosinus 1 are just something. It's really hard to say what it measured, but yeah, it doesn't have really a correlance with the measurement of the digital thermometer. So that were the results for evaluating the sensor. If we discuss that, there are some advantages. You have 2 vital signs in one device, which not many of these devices can do. Then you have a high quality of the heart rate measurements, which is quite nice to have. You have reasonable body temperature measurements if the environment you are in is stable, if there is not wind or rain or it's cold or really hot. And something which is not correlated to the measurements, but which is also really important, you have an open source Bluetooth API, which allowed me to build the system as well. And you have a long battery life, which is also important to have continuous measurements over a long time. Then disadvantages, of course, the effects of the environment on the measurements. Then the differences to the commercially available thermometer. And there's something which is also quite important, that the wearing comfort can decrease the longer you wear the sensor. So the longer it is in your ear, it can become a little bit painful, which is also not too nice to have. But in conclusion, heart rate measurements are reasonable, and you can also use the body temperature measurements in the end for the classification, because they always behave in the same tendency. So if there is wind outside, the drop of the body temperature is always the same. If it's cold outside, if it's 8 degrees, it always drops to the same amount of body temperature. So you can still use it for the classification. Even though it's not accurate, it's still always the same. Exactly. So that means for my first objective, we can say, okay, that is done, that worked. Oh. Yeah, that worked. So check. We can go on to the next 2 objectives, which are the architectural concept I derived. So we have a sensor which measures my vital signs. We need some kind of server who does the heavy computational part for the machine learning algorithms, and we need some kind of bridge in the middle, which is a mobile application to, first of all, bring the measurements from the sensor to the server, but also to have an interaction of the user with the whole system. So we measure the vital signs, we send them to the mobile application, we display them to the user, we send them to the server, we do a training of machine learning algorithms, and after the training we send the model back to the mobile application, and then we can do anomaly classification and the display of the results again on the mobile application. As well, there should be some kind of user feedback mechanism, because if you have anomaly classification here, which is false positive, you really don't want that. So if you have a false positive classification, you actually want that this data goes back to the server and will be used in future for the training of the algorithms as well. So that was my idea of the concept. That was what I wanted to implement. And in the end, I came a little bit up with a different prototype, which has some differences. You can see here the cosinus 1 as the sensor. We send body temperature and heart rate to an Android application. We display the results. We send also the measurements then again to a Python server, which was developed with the Django framework. And then we do the training of the algorithm. So that's all the same as in the concept, but then I started also to do the classification later on the server, because it was just another layer of complexity to send the trained models back to the Android application, where I would have to use another programming language and to port all the parameters would be another layer of complexity. So we sent back the classification results and also displayed them on the Android application.
One question?
Yeah.
How were the anomalies labeled then? How were they identified?
I will come to that later, probably. Or you can ask again, but I guess I will answer that later. So, discussion of the system. The system allows continuous monitoring of vital signs, which is like the first step, what we need. Then, from the concept, we actually have a high resilience against network failure, because after training of the algorithms, we don't really need the network anymore. We can just train. We can just identify anomalies on our mobile device, which is like really independent of internet connection. And we also have the user feedback, which is really important, I guess, for not having false positive classifications. Then I used the REST and Bluetooth architecture in the prototype, which actually allowed me to build a quite modular system, which is quite extensible and interchangeable with different parts. So you can change out anything, put other databases, put other things inside, which is really important for future use. Then disadvantages, of course, you need a mobile phone, which like decreases your freedom of movement. And sometimes your mobile phone is in your bag, you left it at home, so it's not really. There could be better solutions, and of course there are the differences between the concept and the prototype. So no classification on the mobile device, and there's a missing user feedback. So as a conclusion of this part of my thesis, we can say that the system can continuously analyze and learn in real time changes in physiological response patterns. We just don't know yet if it's like correct or not. So again, for my objectives, this is done, and we can check this, and we can go on to the machine learning algorithms. So when we talk about health data, we normally have like this big problem that you know how normal health data looks like, but it's really hard to generate for yourself like abnormal health data. You are normally like not sick. When I was here, I was like healthy, so I had this problem of I don't know how abnormal health data looks like, and that has as a consequence that I cannot use supervised machine learning algorithms, because I just know half of the data, how it looks like, and I don't know how the other half looks like. So I could only apply supervised, unsupervised, or semi-supervised algorithms, which were developed for anomaly detection, and I came up with these 4 algorithms: local outlier factor, isolation forest, one-class support vector machine, and autoencoder, which are 4 algorithms which are really based on different mathematical approaches. And because this is the Gambis group, I thought, and these algorithms are not really known, I guess, or not as much as the supervised ones, I could go just quickly through them. So the local outlier factor is a density-based approach. You compare the local density of one measurement against the density of its closest neighbors, and then if you have a low density, it's probably an anomaly, and if you have a high density, the point belongs to a cluster. You can see that here on this illustration. So here in the middle, you have the point which you want to evaluate. You look at its 3 closest neighbors, and as you can see, the density of these neighbors is a lot higher than the density of this point, so we can probably say that it's an anomaly, irregular data. Yeah.
But the density in which space are you plotting these points?
How do you mean?
Like in the principal components? Or
No, that's just a 2-dimensional plot of, that's just an example. So these are 2 dimensions, and then you calculate, you look for the largest distance to the points here, and so you have, if you look for 3 close neighbors, you calculate the largest distance to the farthest of these 3 neighbors, and that's actually your local reachable density. And then you do that same, you take the average from the other 3 neighbors, and then you see that the local minimal reachable density is a lot closer or a lot smaller here for these 3 than for this one. So actually the circle shows you the density.
I think maybe I'm asking a more math question. want to say how abnormal is that signal in comparison with others? Like how do you find distance if you have
like
not that point? Like how do you put that signal from your sensor in kind of a map and then measure a distance?
It's just a multi-dimensional space then. Also, if I understand the question correctly, it's here you have just 2 dimensions, so we can take any distance measurement for these 2 dimensions, and then if you have 45 dimensions, which is 54 dimensions, which I have in my time series, then you have just to calculate the distance on these 54 dimensions. Is that answering your question?
Yeah, I think you have to check the specifications.
Yeah, exactly. The formula describes it more. Yeah. So the next one would be the isolation forest. It's a distance-based approach. It's actually an assembly of decision trees which try to isolate one instance from the others. So if you have a short path or like just a few decisions to take to isolate an instance, it's probably an anomaly because as you can see here, x0 is here, so you need 4 decisions until it's isolated. And if you have a long path, it's probably normal data because as you can see here, you need 12 decisions until you can isolate x, y. So if there is really a cluster of points, it's really hard to isolate them. So the path and the decisions will be higher, and it's probably not an anomaly.
And one of the parameters of the model is the level of isolation.
Yeah, exactly. Then the next one is one-class support vector machine. It's based on normal support vector machine approaches. You all know how a support vector machine works. You have the input space, then you use a kernel function to transform it to a higher dimensional feature space, and then you try to find a hyperplane here in the middle, which has the optimal distance to the both support vectors. And this allows you then to separate data, which is actually in the beginning not linearly separatable. In the case of a one-class support vector machine, you don't have like 2 classes, as you can see here. You just have 1 class, but you still do the transformation on a higher feature space, and then you try to find a hyperplane which separates the data you have as the normal data as good as possible from the origin. So everything which is like on the left side would be here an anomaly, and everything else here is your normal class. And the last one is the autoencoder I chose. That's an algorithm which is based on neural networks with multiple layers. It actually consists of 2 networks which you put together. You have them with a symmetrical design. So you have the encoder. It tries to find a reduced representation of your data with the most important things to store it. And then you have the decoder, which actually tries to reconstruct the data again. And in the end, you get the reconstruction error. And if the reconstruction error is really small, you probably have normal data because the algorithm was trained to do a perfect reconstruction. But if you have a high reconstruction error, it's probably an anomaly because the algorithm doesn't know how to reconstruct the data. So it will be there will be a high reconstruction error. So that's what the autoencoder looks like. You have here on the left side the encoder, the decoder, and here is the important representation in the middle. Exactly, so that were the algorithms. Then, of course, I had to evaluate these algorithms. So I had to generate the data first. I chose to measure heart rate and body temperature for 72 hours in 5-second intervals. So I had in the end 65,000 measurements. Then I generated time series of a length of 2 minutes, each 25 values for each vital sign. Then I used also statistical features like the mean and the standard deviation, and added also the hour and the minute. And then I just chose all the time series with an overlap of 30 seconds. So that allowed me also to find changes which happened in the boundary events. Because if I just use each like time series after another, and there is a change exactly on the boundary, I wouldn't see that change in my evaluation, and there would be false evaluations. So then, of course, as I said before, I had the problem, what will I use to evaluate my algorithms, because I didn't have like any abnormal data. So because I also had to label my data for the analysis of the sensor, I said, okay, I'm just going to use different labels as abnormal data and some labels as normal data. So normal data was just like daily activities, sleeping, lying, sitting, walking. And then I used as abnormal data sport, eating, and when I was in the metro here in Santiago, because I was like a really short time of this 72 hours, so I had this disparity between a lot of normal data and just a little bit of abnormal data. Then I trained the algorithms using a data-driven approach, so that means I just used all the data at one time series and put it inside. I supplemented this by the statistical features from before. Then for the training, I just used all of my data I had as normal, except a little part which I used also for the test set with the abnormal data, so that I had a 1-to-1 ratio between normal and abnormal data in the test set. And then I used grid search to find the best parameters for each algorithm. Then I evaluated the algorithms using a confusion matrix to calculate accuracy, sensitivity, and specificity. First, the overall results, putting all abnormal data together, and then also for the specific results for each time of abnormal data.
How do you balance the classes? Like manually? I mean, you train with half each time.
No. I just used all my normal data as training, except like randomly pick out or don't use the same amount if I have as abnormal data. So if I have 10 samples for normal data, I have one sample of abnormal data, I use 9 samples of the normal data for training, and then 1 sample of abnormal and 1 sample of normal data for the test set, which was not used before in the training.
So the training is unbalanced? The training?
Yeah, the training is just all I have. Yeah. Exactly. Yeah, so these are the results in the end. The results are all quite well, I guess. We have like everywhere for the local outlier factor over 86%, same for the isolation forest. One class support vector machine was also really good, over 87% for all 3 types. The autoencoder was a little bit bad, but still with good results, like 3 of 4 time series could be identified correctly. In the end, it showed that one class support vector machine was the best one, but yeah, the other 2's isolation forest and local outlier factor were also really good overall. When we look at the specific results, it's a little bit small, I know. For the type of sport, results were really good. I mean, sport is really obvious to detect because heart rate rises, body temperature rises, so we have almost like 95%, 93%. So it's for all algorithms, it's really good. If we look at the metro type, isolation forest and one class support vector machine were better in comparison to the eating type. So it's maybe we could say that these 2 algorithms could better identify metro, better identify changes in body temperature. And the other 2, local outlier factor and autoencoder, could better identify eating, where you have a little change in heart rate, but you don't have it, or maybe you have a change in body temperature, but only if you eat like really hot food. So yeah, in conclusion, for sport, one class support vector machine was best, for metro the isolation forest was best, and for eating the local outlier factor performed with the best results.
How do you combine the 3 measurements to say this is the best? Because I see the isolation forest to be 100% in sensitivity, I think.
Yeah, so I just looked of all over. I just looked over all of these three and I said, okay, the best for accuracy was local outlier factor, the second best was, and then I combined it all together. Then instead. Yeah, so discussion, advantages. It is really important for these algorithms that they consider the inequality of the data, because you have a lot of training data and you don't know how the irregular data looks like. So this is really important that these algorithms can work with this kind of data. Then you have a fast computation using a data-driven approach, which is for time-critical analysis of health data really important. You have algorithms of different mathematical approaches which you can apply, which all work more or less. And then, of course, you have a high accuracy and sensitivity and specificity for all three types of data. Disadvantages, most of the errors for eating and meteor are actually on the boundary. So if you go into the meteor, it takes a little bit of time until your body temperature rises. So until this time or this sequence is over of change, you will have a false classification. Then, because I had 2 minutes of interval which I looked at, time series length, you always need half of the whole time series to actually get good or correct classification, because if you just have half of the measurements, it cannot detect that there was actually a change.
Do you consider exercise as anomalous data?
Yeah.
Okay. Because if you have a fever or something, it will be similar to exercise, because your temperature will rise and your heartbeat will rise.
But probably not as fast as if you do sport. I mean, if you do sport, it's like I start sport, and 2 minutes after sport, my body temperature already is higher. But if you get a fever, it's probably a lot slower, and then it needs some time until you can detect it. But fever is not so time critical. If for something else, it would be maybe, yeah. It always depends on how big your frame of what you look at is. Exactly. So, and last, which is actually a problem in medicine, I guess, is all these algorithms work on best accuracy. So you want to have all the algorithms were trained to have a really high accuracy, and they don't care about sensitivity and specificity. So you don't have the ability to move your threshold to the left or to the right to say, okay, I don't care about accuracy. I want to have a high sensitivity or a high specificity, except if you, okay, this graphic is not so good visible, but this is the reconstruction error of the autoencoder, and as you can see here, this is the threshold to decide if the data is normal or abnormal, and the red one is abnormal data, reconstruction error, and the green one is for normal data. And now if you would move the threshold to the left, you can really easily increase the sensitivity of the algorithm, that you want to say, okay, I don't care how many negative or wrong classification for the normal data I have, I just want to have all of the abnormal data classified correctly. Or you could use, move it to the right, you can increase specificity, and then you want to say, okay, I just want all the normal data has to be classified correctly. I don't care about if I miss some abnormal data in my classification, which is really like important, I guess, for medical systems. So, in conclusion, all algorithms have an accuracy of over 80%, which is quite nice. So we can say this was implemented too, it works. And in conclusion, I would say, because all of my objectives were done successfully in kind of a way, we can also say that my hypothesis, which I asked in the beginning, is kind of supported. So that means a system like the one I developed can identify changes in physiological response patterns. But of course, there is always a but. There are two really big limiting factors. So first of all, for the experiments, all the experiments I did just on myself. So there is one person who did the experiment. So there is no really statistical meaning in all of that, because just because it works for me, it doesn't really mean that it would work for anybody else. So the thing is that my experiments, to show that my hypothesis really is true or could be supported, we would need to do the same experiments with other people. And the second thing is, for the machine learning algorithms, I just showed that it works for different activities like metro and sport, eating, but that doesn't really mean that it will work for changes which come from diseases. So you also would need to kind of evaluate the system with disease data, but in turn this is again really hard to generate.
It would be interesting for me as a female, because females have temperature differences during the menstrual cycle.
Exactly.
Would it identify this because you have so small parts of data, so you have the difference just in a small time? Will it identify it over a longer time?
Well, there are actually some products on the market at the moment which can be used for ovulation tracking when it's the best time.
But will it identify it if it's is a disease, or is it just menstrual differences? I think that would be something important for female users.
Yeah, I guess in the end it depends on your training data.
Okay.
How long you train your network, how many.
And we're talking about tenth of a degree.
Yes.
So if you want to have kids anyway.
Well, I guess
the
though.
fever is something different. It has to be about 38. You never reach.
Yeah, so in the end it's always a question of your sensor, right? If your sensor can do 1/10 of a degree's difference and measure it correctly, and you know it's correctly, maybe, we don't know yet, because I even don't know why it could identify eating from normal sitting, because the changes are really small, but it was actually possible to see it. So the question is, why could it see it? I don't know it. I haven't had time to identify that.
Estimation would be your muscles while chewing are getting more, and this is quite near to your ear.
That could be, yeah, maybe.
It's an estimation. But talking about the temperature, you were talking about body temperature, but actually this device is measuring surface temperature, or kind of surface in the ear temperature, and doing assumptions about your real core temperature. So as a nurse, there's only one place where you can
I know.
real core temperature, which is not convenient. So that's why you do it like that.
Yeah.
Yeah, okay, I don't judge.
Yeah. So, we said that already. So, just to finish my presentation,
Did you see if the error in the sensor temperature generates some error in the classification?
Sorry?
Because the error of the temperature sensor, because you observe that you have a lot of differences.
Yeah.
When you go outside, it's very low and then very high, and this should generate a lot of error in your classification.
No, not really, because it always changes the same way when you go outside. It didn't matter if it was like minus, or if it was 0 degrees outside, or if it was 8 degrees outside. It always dropped around to 32 degrees, and then it stopped there. And then if you went into the sun, it always rose to around 36 degrees, 37, and it always stopped there. So the tendencies of wind, of cold weather were always the same for the sensor. So it didn't really matter how the sensor was wrong, because it measured the data always in the same way wrong. You know what I mean?
Consistently.
Yeah, exactly.
But when you are in the boundaries, you don't have this. I mean, when you are going out and the temperature is decreasing, it's generating some outlier for you.
No.
should be. Yes.
Not if I know that during training.
Yeah, but the point is when you really have a decrease of temperature, you will say that it's not an outlier.
It depends how steep it is, or how fast, or how the change is. If the change is exactly the same way it is when I go outside, then it will not be an outlier, then I will miss it. But I think it's not really reasonable that the temperature will drop.
In the window you are seeing in 1 minute, you don't see these differences.
Yeah. I don't know. Well,
You didn't check that?
no, I didn't check that. Yeah, that's another weakness of my thesis, I guess. So just a little bit of outlook in the end. So because there was really like a beginning work of working with sensors and trying to use machine learning algorithms on them for health data. So you could use more data sources which are like medical and non-medical. You can use respiratory rate, or you could use the location sensor, acceleration sensor, like it is done, for example, with the Apple Watch now, that you can detect falls with the new Apple Watch, which is also based on the acceleration sensor. So this would probably increase the detection accuracy of your algorithms. Then you could like do some system extensions. You first of all have to implement the differences between the prototype and the concept, of course, to have it like maybe use it as a productive system, but you could also use, for example, the smartwatch instead of the mobile phone. The new smartwatches as well have like internet capabilities, so that would probably increase your freedom of movement. Yeah, and another possibility would maybe to add an alarm hierarchy, including like maybe as well third parties or family members, that if the person who has an abnormal health data could identify someone. And last but not least, of course, for the machine learning algorithms, you could compute more statistical features in the beginning. You could test other algorithms, more sophisticated neural networks, for example, a convolutional neural network or a long short-term memory could probably increase the results of an autoencoder. And you could also play with the analysis time frame, that like you don't look at only 2 minutes, you look at 1 hour or at 1 day, or yeah, you just try to identify long-term changes, short-term changes, whatever you want. So there's a lot of possibility to play around. So yeah, I guess that's it. Just to finish my presentation, I want to say thank you, first of all, to my professor, Jocelyn, Stefan Hertel, and Professor Figler, who is not here anymore today. But I also want to say thank you to Stefan and Pilar, who helped me a lot during my time in Chile, and just to everybody who like made my stay here in Santiago an incredible time. I will never forget that. So thank you very much. And if you have questions now, more questions, please. Yeah.
Did you consider for the decision making a quorum of multiple algorithms and analyze the accuracy of a quorum of multiple algorithms in comparison to a single one?
I thought about that, but because all algorithms are showing similar results, it was not really feasible to do, but it would be a possibility. Yeah. But then, of course, you have to train all of the algorithms, which also needs more computational resources again, and there's always a trade-off.
Yeah, Little, first of all, very nice work and an excellent presentation. I think it's like a Model X presentation of what I would think master thesis needs. Difficult to say what can be more perfect than what you did.
Thank you.
So all the master students take notes of the rhythm and of the kind of analysis, I would say. So really happy to see a precious work.
Thank you.
Now I have like tons of questions. Maybe first of all, be careful when you have a nice hypothesis and finally you have to reject or to approve, no?
Yeah.
And you said kind of.
Yeah, well, I can support it for myself, the hypothesis, but I cannot say that it has statistical meaning.
Yeah, no, it's you. It's just you that has been the object of interest.
Exactly.
And, that was like my second question. You did a lot of work in setting up the system, in controlling everything, but you just checked yourself.
Yeah.
And that would be but infinitely more interesting if there were just more people data.
Of course.
What do you think about that? Will you be switching your subject now? Because you have like set a framework to work, and many people could step in.
Yeah, so if somebody wants to use that as a future master's thesis, it would be
it's
possible.
Like trying to please use me, give me more of these sensors and get other body temperatures measured in parallel and start to play around, because it's nice. So but you say that this was C-test, now I switch my subject and I will focus on another subject? Or what is the general, because it's like sad to see that this is where you have it and then say, okay, I will switch my subject and that's it.
Yeah, so.
What do we think in general? Especially, I don't know.
Yeah, well, my studies are over now, so I hope they are over. Of course, it would be really nice to like go on with this, but
are you going in Heilbronn? Will you keep using that rhythm of work?
What's the rhythm of work?
No, will you use this kind of analysis sensors?
I think the idea was we were working on this our bachelor course, thinking about this theme and would it be possible to do something like this. It was because of identifying abnormalities, to identify epileptic.
Yeah, so the thing came actually in the beginning from epileptic seizures, where you also have a change, where it would be really nice to see or to identify when will a next epileptic seizure happen, because sometimes in special kinds of epileptic seizures you have this change in body temperature too. So, but it's really hard to jump directly to medical field and say, okay, we want to go to epilepsy and this is going to work. And so that was like exactly. So we
did a very technical work.
It's a very rare form of epilepsy, so there's not much funding or interest in general. That's a problem.
And a problem I see is that if the sensor is not nice to wear, like for a seizure, you have to just wear it like for 3 years in case you get one event.
Yeah, but.
And also you are analyzing the temperature, which is the most noisy signal from the sensor, because the heart rate is already checked.
Did you always have the heartbeat analyzed in parallel?
Yeah.
Heartbeat was always within the data.
Yeah.
And that was why it was so easy to detect sport.
For example,
I mean, forget temperature, just take heartbeat.
And
Did you check perchance the relationship between the different classifications? I mean, you have some incorrect cases between all the algorithms. Did you check which signals were those cases? I mean, if the different kind of machine learning experts told the same results across the different examples that you did?
No. If I understand, yeah, it would be interesting to see, but there's always this time limit you have to consider. Yeah, exactly. There's so much to do in the future with this, or I have so many ideas how this work could continue, but yeah, somewhere you have to say, okay, this is my master's thesis, And that can go on after my master's thesis, but I have to like somewhere make a cut and write it down and then see what comes to the future.
Do you find the ear sensor really convincing? Or will that be integrated to a phone, to a wearable?
Well, to have it in the ear is actually, so when I was wearing the sensor for like 1, 2, 2.5 hours, I really started to forget that it was here, because you can do anything you want with your hands. But after like 4 or 5 hours, you're like, your ear starts to feel that there is something always having a little bit of pressure everywhere, so it gets uncomfortable. But overall, the sensor is a really nice thing, so it's really...
But now you have the Apple Watch.
I don't know if the Apple Watch could measure body temperature, for example.
It's skin surface temperature, which is very inaccurate, and there's no here. It's the only.
The ear is more protected
Then the watch, which is keeping in touch with your arm. Do we suspect or do we know?
I'm pretty sure because it changes much more the temperature. How much?
I don't know. Do you know that or you think?
I know that the watch itself changes temperature. For example, when you use more CPU power, then it gets warmer. So it's not possible.
Google says that it measures temperature.
No,
Yeah.
It doesn't, but it changes.
It doesn't. Internally for throttling the CPU.
Yes.
Yes, Patrick says no.
But there is an app called
So it doesn't-
ThermoWatch.
That's.
I think that
For Apple Watch.
I always think in the clinical area. So maybe in the run it would be nice in the future to take. There's one group people where temperature is really important. That's our the chemo patient, because you're gonna put chemo in a patient with even a little bit of fever. And high run is with B2 working with the oncology service, with the hospital, so that they are very integrated to studies and the temperature of the patients with chemo.
But that would be Patrick's choice of the temperature detection.
No.
Yes.
What kind of, sorry, I was
Googling.
Googling it. What would be my favorite?
No, but Tila says in the chemotherapy,
Yeah.
temperature measurements are very important,
Yeah.
and even slight temperature
Yeah.
changes might lead to whatever.
Yeah, the question is, do we need continuous temperature measurement? The question is, do we need continuous temperature measurement, or is it enough that the patient's smartphone or smart watch reminds him every 2 hours or twice a day to do it manually with the internet connected in-ear manual feedback? If you want to do continuous, yeah.
We are only taking the temperature before they arrive to the chemo center.
Yes. Yeah, but that's easily doable with a connected delivery.
It's a hard word to say.
Temperature measuring device.
Maybe you need a very sensitive thermometer in the place where you are taking the chemo, just before, you know. I don't know if you need to have it the whole day measurements to like predict.
Because if you have the chemotherapy, like there are cycles, and they have 20 days. So if you know, for example, 2 days before that a patient needs the chemo this day, and the patient is telling you that has a little bit of fever, and the patient can detect it, you can maybe treat it before, do antibiotics, and do the chemo cycle after, not suspend the chemo cycle. So that can be possible.
Just saying.
You can also use it with premature babies because they cannot control their temperature, and they also, in the chemical surfaces, the ambient is controlled. You know the temperature where you're putting those babies, so it can also be used in those patients.
But they nowadays, at least in Germany, get permanent rectal sensor. recto-anal sensor. Yeah, because
It's very accurate.
it's so accurate. And there's that one use case selling a lot, not a lot, but making a certain amount of money, which is Bluetooth-enabled patches with thermal sensors for babies which are having seizures because of fever.
Yeah.
So if you're a parent and you want to wake up, if their body temperature rises because you know that possibly it will start to have a seizure, then you can apply this patch for some days, and they're quite accurate, but you throw them away. They have a lifetime of 1 day or 1 week.
It's actually the same sensor company which made the Cosinus one. It's also another. It's really new. It just came out a few months ago to measure really accurately. They say it's more accurate than the Cosinus one, but the Cosinus one is not really accurate. So, or in my case, so
But
yeah.
if you have a baby, you put something in his or her ear, it will remove it.
Yeah.
And the patch is more secure.
Okay. So, but they have such a sensor too for babies.
They are, yeah. But the most of them are not open source.
Yeah, yeah.
The communication protocol is closed source because it's
Of course. That's too bad.
Is there a collaboration between Heilbronn and the company that makes the sensor?
No.
So why Christian is giving the thesis, like, check this sensor? It looks like they will be very interested if there is development of uses from their own sensors. Like, the company will be the most interested, I think, in this.
I don't know.
Their focus is sports most.
Yeah, their focus is sport. Triathlon, it's called. So, I don't know if they are interested.
To get a Medizinproduktgesetz compatible device in Germany, which is German stands for a regulated medical product, and it's really hard to get it or cost intensive, and so it's easier to make money with sports than with medical devices.
Yeah. So if there are not any more questions, thank you again. And